So in this video, we will be performing a von Neumann stability analysis of the Crank-Nicolson method that we used in the last video to prove that there is indeed no constraint on the choice of dx and dt with regards to stability. So as you can see on the board, I have our equation from the last video, and then I also have the equations that we derived in the third part of this series for tjn, tj plus 1, n, and tj minus 1, n. If you don't remember how we got those, you can look back at the third video in this series. But all this is going to help us perform this von Neumann stability analysis on the Crank-Nicolson method. So in this video, to perform this von Neumann analysis, we're going to be wanting to compare a temperature at some position J and then a temperature of n plus 1 compared to a temperature at the same position J but at the previous time n. And then these two temperatures are going to be related by some factor. We can just call it like omega. And we're going to want omega to be less than or equal to 1. And what this means is that using our von Neumann analysis, it means that our formula from the Crank-Nicolson method will be stable when that omega value is less than or equal to 1. So now what we're going to want to do is get this right hand side in terms of j to the n plus 1, and then get the right hand side in terms of t sub j comma n. So for the right hand side, t j, but we want it in terms of j n plus 1. So we're going to be factoring that out. And then, so this first value, we're going to have negative u still there. And then how we relate this j plus 1 to the j, we can use this equation here, where we have e to the ik delta x, and that's what we'll be relating this to that. So again, we'll have e to the ik j delta x. And then this already has the tjn plus 1, so it'll just be plus 1 plus 2u. And then this will be u. And then this time, since it's j minus 1, we're going to be using this where we have the negative in the exponent. So e to the negative ik delta x. We actually don't need the j here. Because again, it's this right here that is relating these j plus 1s to the j. So that is that side done, and then now we can do this side, where we want it in terms of t j comma n, and this time we have u, and it's going to be basically the same as up here, like that. I did notice something I had wrong in this original equation. This should be minus, so then it would be minus here as well. Minus and minus. So again, we want the left-hand side to be just tj, n plus 1. So what we're going to want to do, again, these are set equal to each other. What we're going to want to do is divide this by this in order to get that on its own side. So I'm going to do that really quickly. And we also will be using this equation that we also used in the third video in order to simplify these e to the I k delta x's. So again, on the top will be this, so it'll be something like, we still will have this t sub j coming in. And then on the top here we'll have 2u cosine k delta x and then plus 1 minus 2u, and then on the bottom negative 2u cosine k delta x plus 1 plus 2u. So now we can factor out 2u on the top and the bottom. So this will all stay the same. But now on the top, we will have 1 plus 2u, and then cosine k delta x minus 1. And then on the bottom we'll have 1 plus 2u, 1 minus cosine k delta x. And now we can also rearrange the top so that this portion is the same as the bottom. So if we do that, we will get 1 minus 2u on the top now, and then 1 minus cosine k delta x. And again, the bottom will stay the same. So now finally we can just evaluate this expression that we have obtained. And the first thing that I want to highlight is this u here. And again, we have that equation for u. It just has omega, delta t, and delta x, which are all positive. So that means the u will always be positive. And then if we look at cosine x, that's always going to be less than or equal to 1 or greater than equal to negative 1. So that means that our expression here on the top and the bottom is always going to be positive. So we can rewrite that as its own variable, and we're just going to call it omega again, so 1 minus omega, 1 plus omega. And again, that omega will always be positive, so that means that this temperature here, if you do 1 minus positive, 1 plus positive, it'll never be greater than 1. It could equal 1 if our omega is equal to 0, but it'll never be greater than 1 And that means that our temperature will never go to positive or a negative infinity, and we will have a stable solution.